Let's go. Okay, so today we're going to go, well, last day we talked a little bit about crossed random effects. I'm going to go back over that with an actual example that illustrates at least one scenario where you can, by taking account this extra thing in your model, you can actually get more accurate representation of reality. So we've got our folder here, HMGX, hierarchical mixed design. So there's both within and between variables, Gaussian for G, X for crossed. I'm going to open up the project, hmgx.rproj, and I'll open up the R file hmgx analysis, which starts off by, as typical, we load up all the things that we want, including the new easy stan, which, and we'll load in some data. Take a look at it. So this is data where, okay, we've got 1, 2, 3, 4 columns, an ID column that has a bunch of observations under the category 1, a bunch of observations for 2. So ID is the subject in an experiment, and there's a bunch of subjects. I think I have 100 in here, so really high end. We've got a column called word. We've got 1, 2, 3, 4, 5. It goes up to 10 for subject 1. Goes 1, 2, 3, 4, 5. Goes to 10 to 2. So word. I talked to you the other day that crossed random effects is something you see very commonly in linguistics type literature, psycholinguistics. So this is the scenario I was imagining, that we're doing some sort of experiment where each participant gets exposed to each of 10 words. I haven't told you what the experiment is, though. We've got another column here called stim, and we see clear degraded, clear degraded, clear degraded. So for each combination of word and person, there's 2 levels, clear and degraded. So this is an experiment that I kind of mentioned the other day, very typical in linguistics or psycholinguistics, where you might be interested in the internal processing of words. So you present both words and non-words to people, and you measure how long it takes them to categorize them as either word or non-word. And you might manipulate the stimulus qualities. So you might either show them as clear or degraded. Now, I've taken off the signal detection type data where what response they made, either yes, that's a word, or no, that's not a word. If you actually had that sort of data, you'd want to analyze that. I've narrowed it down to just the words, not the non-words. So in theory, we've got some sort of measure. I actually didn't put these values in the proper realm to be reaction times, so but let's just pretend they're reaction times. Maybe I've got a different kind of clock. So reaction times typically are, for that sort of thing, is in like the 200 to 300 milliseconds, whereas these are all going to be around 100-ish. In any event, we've got, for each word, 1 observation from the person when it appears as clear, and 1 observation from the person when it appears as degraded. So prior to learning about this concept of cross-random effects, we would have just used a hierarchical model reflecting the fact that, ignoring word, we could have computed for each person their overall reaction time across stimulus conditions. And then we could have computed the difference between their mean reaction time in one condition and mean reaction time in the other condition. So we could have, for each person, computed an intercept and an effect. But we also actually have individual observations, many observations within each condition. So we can estimate the measurement noise. And I'll maybe start drawing. So for a given person, we might have our outcome, whatever it is, y, and clear and degraded. And we might compute the mean in clear and the mean in degraded. And so for a given person, we can compute what the sort of intercept point is, the halfway point between the two, and we could also compute what the difference is. So I'll say intercept here and difference there. But we actually have a whole bunch of observations within each of these points here. So we can also estimate out what is sort of the magnitude of measurement noise. I'll call maybe sigma as measurement noise. So in the model that we're going to deal with, we're going to assume that measurement noise is just constant across people and constant across conditions. So this same amount of measurement noise manifests across both for the same person, but also for a given person, it's that same value. You can relax that assumption and model the amount of measurement noise is varying from person to person. That actually tends to be a good idea because that is something that varies in most scenarios, at least in psychological research. But you can also do things like model a difference between your conditions on the noise, or an effect of condition on the amount of measurement noise you observe. That can happen a lot too, but I haven't bothered showing you about that yet. So far this is all just been describing our standard hierarchical model, where you can estimate sort of something within each person, but then also estimate measurement noise. What's going to change now is that, again, we have each of these observations, and for a given person, each of these observations has the label, it's person 1. This is from person 1, this is from person 1, this is from person 1. But, and in theory, the reason why we're sort of, maybe to back up a bit, if we look at the raw data here, if we look at just the amount of variability that there is across all these observations, and we said, okay, what happens if we actually take into account the fact that there's these individual labels for people? So we compute the mean per person, and we subtract that mean from that person's observations. What that's effectively doing is saying, okay, what would the variability be if we just removed person as a source of variability? That would give us a lot lower variability. So what that would tell us is that person as sort of a unit has a sort of substantial contribution to the overall variability. Another way of saying that is that people have a high variability in their intercept relative to how much other noise there is in the model. So that's why we use this idea that we have a label for each outcome corresponding to what person it came from to reduce what would otherwise be seen as error variability. We don't have to stop there, though. If there's other things in the data set that we think that are contributing variability that we want to be able to, that we know is sort of labeled variability and not error variability, we can similarly subtract that variability so that, again, our model is seeing only what we would want to see as error variability. So again, if we have, for example, well, from the psycholinguistics literature, as I said, they know that words tend to vary sort of strongly from one to another on properties. Even when you try to control things like word frequency and concreteness and things like that, you can still get really strong differences between words, and those differences are consistent from one person to the next. So if you imagine like an ordering of like which words are fastest for person 1, or they have like word 1 is slower than word 2 is slower than word 3, and person 2, word 1 is like, you still get, there might be some a little bit of variability associated with measurement noise, but in general, you get the same sort of trend. Maybe there's sufficient noise that word 2 comes out as faster than word 1, word 3. Like if you actually turned it into ordered data like this, there might be some noise. But in general, across things, you find that there's consistency even across people with regards to the ordering of the words. And I just arbitrarily labeled these as word 1, word 2, word 3. Presumably some word is the overall fastest word, and some word is the overall slowest word, and there's other words that are in between. But the key is that the amount of variability from one word to the other is a large amount of variability relative to the amount of variability there just is in the general data set. So being able to take that variability out is useful. Another way of thinking about this idea of like taking a variable and subtracting out its variability before talking about the other variables is that you're actually interested in something. You're interested in like the effect of stimulus. You're not interested in how people vary from one to another as much. If you're into individual differences research, you might be. But for the main question of does stimulus affect the performance, you're not interested in the variance associated with people varying from one to another. You're also not interested in the variance attributable to words causing performance to vary from one word to another. So you're affected by letting the model know the label for the person and the label for the word. You're able to subtract out that extra variability that you don't really care about so that the model has better precision in talking about the things you do care about. Now, for this particular case, we're not only subtracting out, or we're not only telling the model that people vary in terms of their intercept, but we're also telling them that people vary in terms of the effect. So, and finally, we also have the idea that the intercept and effect might be correlated. So a given person might have a high intercept and a high effect, and other people might have low intercepts and low effects, and that would kind of convey a positive correlation or the opposite kind of correlation. You could do the same thing for word. So you could have it so that word had variability in the intercept, and if you had the same word measured in both clear and degraded, which we actually do in our data here, same words are experienced in both these conditions, then you could actually also say the words differ from one to another in the degree to which they're affected by that stimulus manipulation, clear versus degraded. I haven't added that to this model just for simplicity, but you could do that as well, and that would, again, there actually wouldn't be harm to adding that, and you could get out some interesting things from that. Usually you have like lots of subjects and kind of fewer levels of word, so the more levels of word, the more like parameters you can associate with that variable. We only have 10 levels of word, so it probably wouldn't really be, we wouldn't have a lot of power to see things like a correlation between the word's intercept and the word's effect if we tried to add that into the model anyway. If you guys are interested in actually seeing that full model at some point, another day than today, we can take a look at that. So I'll show you how to prep the data for the model and then pull up the model itself. So as with all the, I think we even started this with the repeated measures stuff, that we want to first arrange the data by ID. We then create the within subjects contrast matrix. So we're just saying that there's a main effective stimulus, clear versus degraded. And there's our contrast matrix labeling each trial as being either clear or degraded. Now, Despite this being called HMGX, so the M implying there should be both within and between, I actually didn't add any between to this. We could add in a dummy variable like sex, but I showed you the trick to using still the same code, the same stand model for a purely within is just to provide just the identity column for the, the intercept for the contrast matrix. So to do that, you just say tilde1. So again, B will be a matrix technically, but it's just a column of ones. So that's just a quick trick to not have to go fetch your hierarchical within Gaussian crossed. It'll make the model actually a little bit slower relative to actually going and using the proper one, but on the scale of the models that we're dealing with, it's not a big deal. So having generated all that, we can package things together in a nice list for Stan. We tell it how many data observations there are in total, so that's the number of rows in the original data set. We give it the list of outcomes, so that's that column, that value. It's going to scale things internally, so we don't need to do that out here. We tell it how many columns are in the within subject's contrast matrix. We give it the within subject contrast matrix. We tell it how many columns are in the between subjects contrast matrix. We give it the between subject contrast matrix. We tell it how many subjects there are. We give it the list of subjects, where we use our little trick here to make sure that regardless of what is actually in this ID column with regards to like the naming strategy for the subjects, this will yield a sequence of numbers where the first level of ID will be called 1, the second level of ID will be called 2, etc. And we actually do the same thing for the words. So we get the unique number of unique words, and ditto pass in the numbers corresponding to the entries in Word. So in the data frame, I actually had literally numbers in here for Word, but maybe you actually literally had the character string corresponding to each word. This would still work in that it would give it the numbers corresponding to each level of Word. All right, so that's going to get passed into the model, so let's go take a look at it. HMGX.stan. Pop out.
I think you have HMGX faster as well.
We'll see why in a moment. So we've got our data declarations, which we just went over. We've got transform data, so we're going to transform to the Z scale so that we can have nice default priors. Just like well, as I mentioned in the diagram, we've got this thing called noise that's just going to be some common amount of noise across all people and all conditions. So it's just a single value. So we define it as being lower bounded at 0, but otherwise can take on any value. We define a coefficient matrix. So as many rows as there are between subjects coefficients, as many columns as there are within subject coefficients, and that's going to, so we're doing inference on the value for those coefficients. For the within subject coefficients, again, because we get a measurement per person for each of the within subjects coefficients, we can talk about how do subjects vary from one another on those coefficients. So we've got the standard deviations for each of those coefficients. And because there's variability on the coefficients, there could be covariability. So we look at the correlation on those within subjects coefficients. Oops. Now, this is when we are doing the model for a hierarchical model, we can express the actual, we eventually need to express that the subject coefficients are sampled from a multivariate normal distribution. So for each subject, we'll get out a set of coefficients for that subject, a set of the within subject coefficients for that subject given their group. So we get a matrix for each subject. There's a set of NW coefficients. The new thing to this model, relative to just the standard hierarchical models that we've had, is that we have two entries here relating to word. So we're saying that the words vary from one to another in their, well, the words have, each word has its own deviation. It causes a deviation, so one word is slower than other words. And there's some variability associated with that deviation. All right. So for our model, we're expressing that this matrix of coefficient means is modeled as just a standard normal on the Z scale, so that's pretty weakly informed prior. Ditto, we've got a Weibull prior on the variability from one subject to another on each of the coefficients. We've got a flat prior on the correlation matrix. And for the noise, again, that single thing, we'll, again, have the Weibull prior. This loop here loops over each subject, and for each subject, expressing that their coefficients are sampled from a multivariate normal distribution, as defined by the correlation amongst and the variability amongst the amongst the coefficients, but also getting out what the coefficient means are, and as combined with what that person's grouping is. So that's what this B matrix is again. It's the between subject contrast matrix. So for that person's group, what coefficients should they have? A little bit here, though, is new. We have these two new things, scaled word SD and scaled word devs, so we need to put, those are parameters, so we need to put priors on them. So scaled word SD, this is the standard deviation of, like, amongst the words. This is, I guess, the standard deviation of the effect that a given word has on the outcomes, so we'll just put a Weibull prior on that. And for the actual effect that a given word has, we'll say that it's centered at 0. So the mean effect of words is 0, but they're going to push half of them are going to push them up, half of them are going to push them down approximately. So it's a normal distribution with the standard deviation that we're estimating, but centered on 0. So finally, as we loop over the observations, we look at each observation and we model it as being sampled from a normal distribution with some amount of that constant amount of noise. This little bit here goes and it figures out for that subject's coefficients, it figures out the subject corresponding to that row, that outcome, gets the coefficients for that subject, and multiplies them out by the actual contrasts for that outcome. So it figures out for that what outcome, what should the prediction for that subject and that condition be in terms of the mean. It then adds to that prediction the deviation associated with the words. So given the word that this outcome is, grab the deviation associated with that word. So that's how we express that the words are having an effect on the overall mean, regardless of what condition it is and regardless of what person it is. Finally, down here in the generated quantities, we've got a section where we just compute all of these things where it's scaled. We compute the unscaled version. So you've seen that a lot in the past. I didn't bother computing a unscaled word SD and unscaled word devs, but you could do that, I guess. So is that fairly straightforward in terms of the way the model is expressed? All we've really added to the standard hierarchical model is that we have, oh, it still looks ugly. We just have these two extra parameters, and they're influencing the model here, where you're just saying whatever outcome would have otherwise been predicted absent any effect of words, add in just a little shove according to what is then going to be estimated for the effect of each word.
So that's the part you call random effects.
Yes, yeah. So again, the terminology used in other domains is that here word is having a random effect on the intercept, like of the overall model. Subjects are also having a random effect on the intercept. Subjects are also having a random effect on the difference between conditions, and we're furthermore modeling the correlation between those two latter random effects, intercept and condition. So I would run this, but you'll notice that there's this HMGX faster. So I actually ran this, well, let's see what happens. So I'm not going to run this because it actually takes a long time. I already pre-ran it, so I'm going to load it up. And let me just see how long it took. About 4 seconds. I'm going to load up this other thing that came from running the faster version. And how long did that take? About half the time. So the C_C is the slower version, _NC is the faster version. C stands for centered, and NC stands for non-centered. That's terminology that you can read about in the stand manual, but the faster version is the non-centered version for this, this model. So why did I do it twice? Well, one of them's faster. I haven't shown you the contents of that one yet. I might show it to you, but I'm not going to go through it. It gets a little complicated.
So hang on, it took 4 seconds to retrieve the information contained within that summary, or it took 4 seconds to run the stand?
It took 4 seconds to run the stand, and actually it took 4 minutes. So this one took 4 minutes, and this one took 2.5 minutes.
Gotcha.
So wall time, they differed in how long it took them to sample 2,000 samples. Well, do 1,000 warm up and 1,000 samples.
2 seconds is not a lot, but 42 minutes is.
Yeah, exactly. Yeah. So one was twice as fast. Let's say get the, how well did it sample noise? Okay, the noise parameter, okay for that one in terms of effective sample sizes in R hat. And ditto for this one. Oh, I guess I didn't unscale this one, but I did for this one. So that accounts for the different numbers you're getting there. But the effective sample size is the same for both, and R hat's the same for both. Let's look at the means. So the means from the coefficient means from the centered version. Well, we get a pretty low effective sample size for the centered version, because there should be 4,000 samples. That's I put it at 4 cores and 1,000 post warm-up samples. I mean, R hat still won. So the different R hat conveys whether the different chains came up with different numbers, came up with different answers. R hat, so the chains didn't come up with different answers. It just doesn't sample very effectively in the sense that there's sort of an autocorrelation. There's relationships amongst the samples that it's come up with. I won't go much into that, any more into that except to say that that's bad. You generally want a good effective sample size as well as an R hat of 1. So let's look at the.
What would be the minimum effective sample?
I like to have at least 1,000.
Ew.
Yeah. So that is definitely too low. Let's look at the non-centered version. Better. Shoot, I shouldn't have overwritten the one where I ran it for longer. It's better. It's like 3 times as big, but it's still not great. We don't care as much about the intercept anyway. Really kicking myself because I actually have a version of this where I ran it for 2E4, which of course meant that it took a half hour for, well, almost an hour, 45 minutes for one and a half hour for the other. And there was a, when I did that, and you can verify this on your own, the coefficient means, the 95% credible interval in this, like the effective sample size was above 1,000, and the 95% interval actually excluded 100. Here it includes 100, but that's because there's really low information, so we don't have a lot of samples actually to talk about the extreme ends. But the 95% credible interval actually excluded 100, but I knew that 100 was what I used as the intercept for that model, whereas the one that used the non-centered actually still included 0. Oh no, I'm sorry. I have yet a third one that I'll talk about in a moment. Yeah. Actually, I should load it up and show you. Post no word. Okay, so C is with the centered version, but again, a model including a random effective word. NC is the non-centered version. It's faster. As I'll show you, it'll have better sampling, and it includes an effective word. The no word one is a model that doesn't include an effective word. The data were generated so that there was an effective word, but the no word is a model that just ignores that source of variability. And that's the one where, okay, I'm going to go back through and say, okay, C, what does that look like for noise? This is a standardized noise, but good sampling. NC, good sampling, and no word. Well, ignore the difference between C and NC in terms of the values here. If I multiplied these by the standard deviation of y, they'd come out to these numbers, 10. If you have, so the main comparison here is between the NC and word and no word. So the NC again contains an effective word. The no word doesn't. So this is showing us that the effective word that's actually there that I included in the model, if I don't let the model see that, it's just going to treat that as noise, i.e. it thinks there's a lot more noise in the data when it doesn't know about words than when it does know about words. So by ignoring words, we've artificially inflated its perception of measurement noise. That actually is going to have a consequence down in a moment, a secondary consequence in a moment. All right, so the means for C are largely similar as NC. NC has a little bit better sampling, still not great on the intercept. I'm not super interested in the intercept, but let me show you what happens when we do the no word, post no rod word. We actually get great sampling of that intercept, except that I happen to know that this 95% credible interval starts excluding the true value that I actually added into the data. So it's you start to get biased estimation. Now, obviously, this is a one-off, and so there was a 1 in 20 chance of that actually happening in this circumstance. However, and I would want to do a little bit more to say that that actually is something to expect. I don't quite understand how that would come about. I don't have a good intuition on that. But anyway, a difference came out between those two, between including the word and not including the word as a random effect.
What do you mean by 1 in 20 chance of that happening?
Oh, well, maybe I'm... Well, because again, if you're saying I'm going to make this decision criteria, a Neyman Pearson-like decision framework of saying if the 95% credible interval excludes a value, I'm going to exclude it as a credible value for the data generating thing. Now, I know what the data generating number was. If I were to repeat this many times and generate many data sets, I was thinking that maybe I could think of this as the 95% credible interval as reflecting the chance that it would include the known value. I'm probably also wrong about that too. So certainly knowing how the data were generated, this surprises me to get a 95% credible interval far away from what I actually used to generate the data. And fairly far, because it's 100 and this span is 6. So it's like a standard, like the size of the 95% credible interval is the distance from the bottom part of the 95% credible interval to what the actual true value was. So the distribution is fairly far away from what I expected it to be. Let's look at the standard deviation. So again, this reflects how variable people are from one to another on each of these coefficients. So post C, good sampling on the intercept, not so great on the variability from one person to another in the manifestation of the stim effect. Let's look at NC. It kind of flips around. Overall, like less effective sample sizes in total, but you can see it's better certainly on the thing that we're interested in. And how about no word? It's actually going to be really good. But it's a much smaller amount of variability that's being estimated in association with the stimulus, the effective stimulus. Now, it actually overlaps pretty considerably at the sort of upper end, but yeah, the overall value it extends to much lower values. The final thing we'll look at is the for the centered on the correlations. Oh, what did I call it in this? Core? What was the correlation in this one? Core map. So correlation matrix, which for just an intercept and a stimulus is just going to be a single correlation. It's estimating that it's somewhere in the negative realm, the correlation. Effective sample size is not great. Let's look at the NC version. Oh, and this doesn't have a core mat. This has something called cores. Same general sort of region. It's generally negative. Much better effective sample size with the non-centered version. Let's take a look at the no word. Very different. So the differences between the no word and the both models that include the word so far have been the no word model sees a lot more noise. The no word model sees, well, a wider range of variabilities associated with stimulus, the effective stimulus, and it's not seeing this correlation at all. It's
say it can be anything. Basically.
Yeah, exactly. Yeah, it's like very uncertain about the correlation, whereas we can be certain at least of the sign of the correlation with the one that actually includes. So you've like missed the whole phenomenon by failing to account for the variability associated with word. Now we can actually check. We can take a look at those estimates for how much the words vary from one to another. These are on standardized scores, so they're Z scores. Right, post and see. So that's for the non-centered version. Here's for the centered version. They both have similar sampling efficiency on both of those. So it's estimating that there's about 0.9 Zs of variability attributable to the words. And if we take a look at the actual estimates for each word, we can actually ask like which are the words that cause positive deviations, which are the words that cause negative deviations. I happened to create the words so that I ordered them, so that 1 actually did have the strongest negative deviation and 10 had the strongest positive deviation. But you can actually see the ordering there in the numbers. So it's accurately picking out their ordering. And I mean, there's uncertainty in terms of there's overlap quite a bit of overlap between a bunch of these, but the overall order is consistent with the way I generated the data. Triple check that how the C sampled these. A little bit better again with the NC in terms of sampling time. So with all of these, I'd probably bump the iterations up to 2E4 so that all of these effective sample sizes were greater than 1,000 for all these things. And I certainly only use the faster version so that it actually compiled in like a reasonable amount of time, or not compiled, but ran through in a reasonable amount of time. I haven't shown you what's in that faster version, so let's take a look now. Same data coming in. That's why I didn't actually have to, oh, I didn't show you, but you wouldn't have to change the way the data was structured. The inside of the model is very different, though. We still have scaled noise. We've got a new thing here, a dummy variable called normal 0, 1. It has, it's a matrix that's as many rows as there are within subjects variables, and as many subjects as there are, as many columns as there are subjects. And consistent with its name, we assign a normal prior on it in the model section. I'm not gonna go through this. You can take a look at it yourself if you want to get really deep into it. In the model, in the manual, there is a section you can search for non-centered parameterization, and that will talk about how this model is mathematically equivalent, but it just it's actually the difference in how it expresses the model. I don't understand how the black box that I haven't told you about actually ends up seeing it as different, because it is mathematically equivalent. It's just faster, and it somehow is able to sample better. That's much deeper than I want to go into with you guys. I wanted to, though, show you that there is this way of making your models go faster when they're not sampling very well, and provide you with this faster version so that if you just want to use it without understanding it, you can. So long as you understand the version that's not the faster version, you can go ahead and use the _faster version, and it is the thing that, it's the same model, it'll just sample faster. I'll also say there are some scenarios where the centered version will actually sample faster than the non-centered version, but that's unlikely for us to experience in psychology. Usually it has to do with like how much data you have at each level of a given sort of label variable. So subject I'm going to call a label variable. In some scenarios where you have like a ton of data per person, I think that's the way it works, or like a ton of people but not a lot of data per person. One of the two switches over so that centered actually is faster than non-centered, but for most of the things I've experienced in psychology, non-centered works far faster than and better sampling efficiency than centered. So, yeah.
Is there any recommendations for running the models all on the same computer, same operating system? If you can report the results?
No, you don't need to. Like, because the critical thing is to just report that you sampled long enough to get a good effective sample size, and that R hat was 1. That should be sufficient. All right. So yeah, that's a little demonstration of why it is important to actually include all the variables that you have good reason to expect have consistent effects on your outcome. Not only people, but also maybe words or whatever might be sort of a uniquely labeled thing in your data set.
Well, what do you think of, because the data set I'm thinking of doing, there's sort of related to this. They have, you have blocks and then trials within each block.
Yep.
Generally, what do you think of adding block as a?
Yeah, if you think that there's systematic deviation attributable to blocks, so blocks are like block
Maybe
label.
they
Do you have a
start
block
their
number?
learning every
one?
block or something.
Well-
1, 2, 3, 4.
So I mentioned this last class,
Sorry.
but no worries. But it's worth repeating, which is that it's most useful to treat something as, I'll come up with a new word, a labeled effect. I don't like the word random effect. I like labeled effect. When you don't have any other data on how that thing could be influencing the outcome. So if I had a bunch of people and I forgot to label their ages, but I forgot to actually collect data on the different people on their ages, but I know that there's variability in my population according to age, and I wanted to be able to at least take out that source of variability, I would treat person as a labeled effect. However, if I did have that age data, I'd actually put that in as a like an effective interest. I'd put that in my contrast matrix,
Yeah.
age, so that it actually, because that's a more direct measure of the thing that I'm interested in taking out at least, rather than treating person as a label effect. If you have something like, what I'm imagining is that you have like block 1, block 2, block 3, block 4, and there's a temporal sequence to block, then I would treat block number as a actual variable that's in the contrast matrix, not as a random effect crossed with person. You could do it as a random effect crossed with person. It's just not going to be as like powerful to see relationships. That might be a good example to actually do like a comparison of the two.
Sure.
If you want to do that as part of yours. What is the consequence of treating it either as a, what would, in the nomenclature, treating it as either a random effect or a fixed effect. When we put things in our contrast matrices, people often use the terminology fixed effect for those things. And when it's just something where it causes, there's sort of random deviation associated with that thing, they call it a random effect. That'd be a cool exploration. But yeah, in general, my intuition is that it's always better to, if you have the actual data associated with the reason why you think that that labeled thing might differ from one to another, put that measured thing in as a predictor in the model. So, for example, I've been talking about these models in lexical data where we just have words. If I knew there was variability amongst the words in terms of their frequency, I'd maybe add, I'd go and I'd figure out what the word frequency is for word 1 and put that there, word frequency for word 2, put that there, and add frequency as a predictor in the model, rather than treating word simply as a random effect. Now, you could actually still treat word as a random effect because there could be non-frequency-based variability amongst the words that cause them to differ from one to another. So I guess it's still okay to add that in. I'll have to think about that because I feel like then suddenly you're causing some potential for confounding. I'll think about that a bit, but yeah.
Sort of along the same lines, is it possible to confound, like if you treat something that arguably isn't really random, like a learning effect or something, as random, could you actually get misleading results from that?
So if word actually truly didn't have an effect,
Or maybe it had an effect that wasn't random, like you're describing, I guess.
yeah, well, the only scenario I can maybe imagine is if, like, maybe I don't know what you mean by random.
Oh yeah, okay, well, I think I've kind of answered my own question in my mind, which is that, so I guess by random I mean that it's not systematic. It's not, you can't describe it by any other parameter.
Mm-hmm.
But in this case, you're saying, well, you can actually say, like, there are differences between the words, such as frequency, that is causing this effect. But
Yeah.
you can still treat it as this, what you call label effect.
Yeah.
And I guess that kind of makes sense because you're allowing the data to speak for themselves, right? You're saying there's
Yeah.
this effect, we don't have a parameter to account for it,
Yeah,
but
exactly.
let it just,
Yeah,
you know,
it's this part of the model where
manifest.
you're saying they have a normal, like, words have a normal distribution
right,
with regards to their
Okay, that
influence on
makes
the
sense.
outcome. Yeah. So that's, I mean, that's one quibble with the phrase random effect, is that it's not, I mean, it's random in the sense that the words are, in theory, they vary from one to another in their effect, but it's actually a systematic variability that one word consistently has this effect, another word consistently has this other effect. Now, they are random samples from the total population of possible words, and that's where that random effect thing comes from.
Yeah.
But yeah, that's, I'm going to start trying to use a labeled effect.
So I'm trying to wrap my head around this for my study, and I have brain folding as kind of the response or dependent variable, and group status. Basically, people have symptoms as the kind of independent variable, and some of those people belong to the same family, so they're siblings.
Mm-hmm.
But some of them might have symptoms, some might not. Treating family AD, would I treat it as this labeled?
Yeah, that's actually a common scenario that might talk about in a subsequent class. Depends on, well, obviously it happens in your data, that where you have nested random effects. That is that you say that families differ overall from one to another, but then you'll have observations within each family of people that might vary from one person to another in that family. They'll deviate from their family mean, and then maybe they also deviate from their, deviate in terms of what their effect is. So you can keep on creating levels of the hierarchy to say that families deviate from one another in terms of their mean, and within families, the people in that family deviate from one to another in that mean. And to the degree that there actually is systematic variability associated with those levels of the hierarchy, the model will represent that by the standard deviations associated with that level. So,
Thanks.
yeah. So I'm going to stop the recording for this because I want to make a separate video for the next part.